Welcome to 53rd lecture in the course of Industrial Engineering and Operations Research. We are discussing an important topic of operations research, that is queuing theory. Already I have conducted 2 sessions on it and this is the third one. So, some theory was told in the previous classes. Now straightway I will start with one problem, because many times, suppose even if you don't remember derivation, but if you know the formula, then you will be able to do problems in competitive exams, because only this type of questions generally come at undergraduate level. So, the question is that customers arrive at a counter randomly every 4 minutes on an average. Determine the probability that the inter-arrival time will be from 1 minute to 2 minutes. So, first question is related with the probability. Customers are arriving every 4 minutes and on average, and then we want to find out whether the inter-arrival time will be from 1 minute to 2 minutes, that is in this limit. If the service time distribution is also exponential with expected time of 3 minutes, find out the percentage utilization of the service facility, length of the system and length of the queue. What is the probability that there will be 2 customers in the system at any point in time? Okay. So, that means, is it 2 or it should be, let us see that, okay, maybe there will be no customers in the system. Often they ask that. Okay. So, let us see that. Okay, we will see that one. Given mean interval time is equal to 4 minutes, hence arrival rate lambda is equal to 1 by 4 customers per minute. So, first you find out the lambda. You are doing per minute wise, so be consistent on minute. Then mean service time is 3 minutes, hence the service rate is equal to, because mean service takes 3 minutes, that means 1 by 3 customers per minute are served and 1 by 4 customers arrive per minute. So, both have to be expressed in the same unit, and both arrival and service time follow an exponential distribution. So, probability that inter-arrival time is from T1 is equal to 1 to T2 is equal to 2, that means it will be P T1 is smaller than T and T is smaller than T2. That means basically you have to suppose this type of distribution is there, T, and this is that probability density function Ft, which is actually used to be lambda E minus lambda T. So, naturally that it goes like this, like this. So, we have to find out between T1 to T2 that area. So, this will be E minus lambda T1 minus E minus lambda T2. Okay. So, therefore, here in this formula, this is E minus lambda T1, it is this one. Suppose T1 would have been 0, then probability that time is less than T2 is basically 1 minus E lambda 2, that means this is this one. So, T1, so this will have become 0 and this becomes 1 minus lambda T. Okay. So, that means in that case it would have become 1 minus lambda 2, that means then I would have said that P, because 0 of course the time is always, so T is smaller than T2 is equal to 1 minus E lambda T2. Okay, that type of thing comes. So, suppose T2 is infinity. Okay, so this becomes P T is smaller than infinity. What is that probability? Obviously 1 minus e to the power minus infinity, that means it is 1. So, I am just seeing that whether, means sometimes suppose you forget the formula, you say that whether it is like that, so you can confirm by these type of things, that whether my formula is valid if T1 is equal to 0 and T2 is equal to infinity, or this is the thing. So, this is what. So anyway, otherwise you have to integrate lambda e minus lambda t, that you will integrate between limits t1 to t2 and you will get this thing. So you have to just plug in the value e minus 1 by 4, lambda is 1 by 4 and here t1 is 1 minute. Okay, units have to be consistent, 1 by 4 per minute, and this is minute minus e minus 1 by 4 into 2. So this thing comes out to be 0.1723. Okay. Now remember, I have written again that Px is smaller than A. That one was 1 minus lambda A. Okay, 1 minus lambda A, that type of thing. So that is why suppose we say time is less than T2, that probability would have been 1 minus E minus lambda 2, and time is less than T1, that probability is 1 minus E lambda T1. So therefore time is between T1 to T2, so you can subtract both probabilities. If you subtract this and this, okay, means you put minus sign here, then you will get this is minus minus will become plus, this will go here and this will go here. So this is how that this one. So probability has come 0.1723. In day-to-day language, we can say probability is 17.23%. Okay, that means very small chance is there that between inter-arrival time will be between 1 to 2. Okay, because generally arrival takes at maybe 4 minutes. Okay, so that is there you will get high probability there. Now utilization, again next question was what? The percentage utilization of the service facility. So here both are exponential distribution. So rho is equal to lambda by mu simply. That is 1 by 4, 1 by 3 is equal to 0.75. Okay, 3 goes there, 3 by 4, 0.7. So therefore utilization of the service facility is 75%. 75% it is utilized properly. Then length of the system. What was the question? The length of the system. That means we want to know L. So that formula is already there. L is equal to rho divided by 1 minus rho. You can remember that formula. Rho is equal to lambda by mu, or you can see utilization factor, and this becomes 0.75 by 1 minus 0.75 is equal to 3. Okay. And then length of the Q. Next question was the length of the Q. So LQ is equal to Ls minus rho. Okay, that means waiting length of Q is the LQ is the number of customers in the waiting. Okay, so LQ is equal to Ls minus rho. That is the formula. So rho is if you do that, rho divided by 1 minus rho, you will get rho square by 1 minus rho. And this will come out to be 0.75 square, 1 minus 0.75. So you get 2.25 customers on an average. Okay, average this one. Although the customers cannot be in the fractions, but on an average this will come. Hence length of the Q is equal to 2.25 customers. Probability, now we want to see that what is the probability that there will be 2 customers in the system. Okay, achha, there is no, it is correct only 2 customers we are asking, not that 0 customers in the system. 0 can be also asked. 2 customers in the system at any point of time. So I want that whether the system length will be 2. So there is a formula. Probability that there are n customers in the system is given by Pn is equal to rho n 1 minus rho. So for n is equal to 2, you put P2 is equal to rho square 1 minus rho, that means 0.75 square into 1 minus 0.75, that comes out to be 0.1406. Hence probability that there will be 2 customers in the system will be 14.06%. Now Q is also called waiting line. So it is basically customers who have arrived but are not being served yet. And system means Q plus service, that means customers waiting in line, including the customers being served. Don't think that if there are 5 customers waiting, then in the system they are 5 plus 1, that means 6. No, this will not be like that. So this is because customers waiting in line include the customers, because what happens that LS is equal to LQ plus rho. LS is equal to LQ plus rho. Rho means lambda by mu. So this will be there. Now let us do the another example. A coffee shop owner runs 3 counters for providing coffee to customers. Okay, suppose it runs three counters. Depending on the number of customers, he manages the number of counters with his workers as shown in the table. Customers arrive at a mean rate of 8 customers per hour. Okay, so rate of arrival is 8. Checkout time per customer is exponential with mean 10 minutes. Determine the probability that one counter will be in operation. That means there will be some customer in the system. So number of customers, if they are 1 to 3, then number of counters in operation is 1. Okay, suppose he has made this type of rule. Okay, table is this one. 1 to 3, that means 1 counter is open. 4 to 5 means 2 is open. More than 5 means 3 are open, 3 counters are open. Even if there are 10 customers, 3 will be open. If there are 50 customers also, then only 3. So how to solve this problem? It is system dependent problem. That means number of customer dependent. Arrival rate is of course constant. It is not dependent on how many people are in the system, because this is mentioned that customers arrive at a mean rate of 8 per hour. Okay. So here lambda n is equal to 8 customers per hour, and n is equal to 0, 1, 2 and up to infinity, any number may be there, but mu n is equal to 60 by 10. Okay. Why 60 by 10? Because it is 8 customers per hour. So I want to convert everything in hour. Here also unit should be consistent. So service rate should be, because here it is written that checkout time is exponential with mean 10 minutes. Okay. So that means one customer takes 10 minutes. Okay. So that means basically 60 by 10. So that means in 1 hour 6 customers go out. Okay, 6 customers per hour. So that must be the service rate. 6 customers per hour, provided your n is equal to 0, 1, 2, 3. Is it not? N is equal to 0, of course, no meaning, but even then you have to say that n is equal to 0, 1, 2, 3. And then suppose there is a, but what happens if the customers are more than 3? That means they are 4 or 5 customers in the system. Then in that case, service rate will be doubled. Why? Because now he will open the other counter also. So 2 counters will be open. So 2 into 6 means 12 customers per hour. And then there will be 3 customers per hour. So that means this is 3 into means more than 5, that means 6, 7 or any number. So 3 into 6, that means 18 customers per hour. So you have got mu 1, mu 2, basically mu n, different quantities. Okay, that is. Now how do you find out that probability? Determine the probability that one counter will be in operation. We have to find out. So we have to do the procedure. First, there is a formula from generalized queuing model. You can see that P1 is equal to lambda by mu. So this is actually 8 by 6 into P0. So that means 1.33. And there are P2 customers in the system, that is 8 by 6 square P0 like that. 3 customers in the system. This one, 4 customers is equal to this one. Use the generalized formula. Up to this it will be 8 by 6, but after that 8 by 12 P0. Then 5 customers in the system. This formula, and this is Pn greater than 6, that means this formula. So the value of P0 is determined by summing all the terms actually. Okay. So n is equal to greater or equal to this one. So this is the formula, and this is equal to this one. So P0 you can do that summation, okay, of this one. So this is equal to this much, okay, fine. So you sum them together, P0 plus P1 plus P2 plus P3 plus P4, and up to that you have to this one. If you know other terms also, it should be added with infinity, but you know that up to this one, depending up to this one infinity, and you do this one. But maybe if you do numerically, other terms may become insignificant also, okay. But anyway, P0, and you keep doing that, and plus 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 dot like that. So you have to do that, and now you have to use geometric series for, because there are some terms which are going up to infinity. So you have I is equal to 0 to infinity, x to the power I is equal to 1 by 1 minus x, mod x is smaller than 1, of course rho is smaller than 1. So you get this type of thing, and you get basically you have to do mathematical manipulation, you can do that, okay, same, and then after that you get P0 is equal to 0.107, you have to see. So probability that one customer counter will be opened will be calculated by assuming that there will be at most 3 customers in the coffee shop. If up to 3 customers, it is okay, 1 customer. If 0 customer is also there, then also the counter will be open. So that means you have to sum P0 plus P1 plus P2 plus P3. That means P0 1.33, 1.33 square P0 1.33. So that means 0.69. So 69% chances are there that only 1 counter will be opened, okay. 2 counters will not be opened. Now so let us discuss some specialized Poisson queues also. Specialized Poisson queues refer to queuing models that are extensions or variations of the basic Poisson queuing systems. These are designed to handle special real-world features such as priorities, bulk arrivals, finite capacity, or customer behaviors like balking and reneging, okay. I have already told these terminologies, that means customers may join but they may leave, okay. Sometimes customers seeing the length of the queue, they may not join. So all those type of models are there. There are separate books also on the queuing theory, okay. So we are just giving you exposure here. This model introduces new features like priorities, group arrivals, customer impatience, feedback, or retries, and state dependent behavior. So there can be, of course, some problem of this type, that there are C parallel servers. So you can arrival rate is lambda, this is up to this is Q, whole thing is system, and this is service. So now here it will be different, that means departure rate here, mu departure rate is like that, there may be C servers. So because we have so many models, so Kendall actually introduced some notation. That notation we can understand. Figure in the last slide depicts the Poisson queuing situation with C parallel servers. The arrival rate at the system is lambda, customers per unit time. All parallel servers are identical. The service rate for any server is mu, customers per unit time. Now the characteristic of the queuing situation is we write by A, B, C / D, E, F. A is equal to arrivals distribution, B is equal to departure service distribution, C is equal to number of parallel servers 1, 2 and infinity, D is equal to queue discipline, E is equal to maximum queue size, finite or infinite. If it is infinite, then instead of E we will put infinity. Allowed in the system, that means in queue plus in service. F is equal to size of the calling source, from where they come, finite or infinite. So standard in notation for representing the arrivals and departure distributions, that means symbol A and B is M Markovian or Poisson's arrival. Markovian and Poisson is basically same. We don't use the symbol P, we use M. All departure distribution are equivalently exponential inter-arrival or service time distribution, and D means constant deterministic time. Okay. If I write D, if I write Ek, then that means Lagrange or gamma distribution of time, or equivalently it is the sum of independent exponential distributions. That much in detail about Lagrange distribution etc. we are not going to cover. Gi is equal to general generic distribution of interarrival time, and G is equal to general distribution of service time. Okay. Now the Q discipline, that means symbol D here in this one, can be different type. So we can use FIFO symbol. FIFO means first in first out, LIFO means last in first out, CRO means service in random order, and GD means general discipline, that any type of discipline. For illustration, the model MD5 and colon GD15 infinity uses Markovian Poisson's arrival. So arrival is Markovian, but D is there, that is why constant service time, deterministic, and 5 parallel servers are there. Q discipline is GD, general discipline, and there is a limit of 15 customers on the entire system. The size of the source from which customers arrive is infinite. Okay, that is why I hold it in infinity. That means size is infinite. Okay, like you have got a very big city, so no problem, people can keep coming. Okay, almost infinity you can consider. Now steady state measurement of performance I have already introduced with these terms, but little bit more systematic I am telling again, so that it becomes perfect in your mind. Commonly used measure of performance in queuing situations are LS, means expected number of customers in system, that you can say system length. LQ is equal to expected number of customers in queue, that means queue length. WS is equal to expected waiting time in system. WQ is equal to expected waiting time in queue, and C is equal to C bar is equal to expected number of busy servers. These measures are derived from steady state probability of n customers in the system Pn. Now suppose you want to find out that what is the system length. You can say Ls is equal to sigma n is equal to 1 to infinity n Pn. This is the expected value, mathematical expectation. That means number can be 1 also, but corresponding probability is P1. Number can be 2 also, corresponding probability is P2. So that means probability acts like a weightage to 2 into P2. Customers can be 3 also, but what is the probability? P3. So 3 into P3, like that. Customer can be 0 also, but 0 into P0, that is nothing. So that is why I have written n is equal to 1 to infinity n Pn. So if you know Pn, you can calculate Ls. This is how it goes. And LQ is equal to what? N is equal to C plus 1 to infinity. This is busy server, n minus C bar Pn. Okay, that means this is based on that length about this one. So relationship between Ls and Ws, that means also LQ and WQ, in fact not LQ, this is Ls and Ws, yes fine, Ws is the waiting time, LQ is equal to queue length, and WQ is equal to waiting time in the queue, is referred to as Little's formula. There is interesting paper of Little also, you can download it, is freely available in the net, but it is of course very simple but very powerful. It says that length of the system will be lambda effective arrival time multiplied by Ws. Ws means waiting time in the system, and LQ is equal to lambda effective into waiting time in Q. So in both lambda comes, there is no mention of mu here. The parameter lambda effective is the effective arrival rate in the system. It is equal to the nominal arrival rate lambda when all arriving customers can join the system. The relationship between Ws and WQ is given by expected waiting time in system Ws is equal to expected waiting time in Q WQ plus expected service time. So that means Ws is equal to WQ plus 1 by mu, because this is the expected service time. If you multiply both sides with lambda effective, then it becomes lambda effective Ws, lambda effective Q plus lambda effective by mu. By Little's formula, this is Ls. Ls is equal to LQ plus lambda effective by mu. Difference between the average number in the system Ls and the average number in the Q must equal the average number of busy servers C. Thus, C is equal to Ls minus LQ, and which becomes lambda effective by mu, and we can say facility utilization is C bar by C. Here C can be number of channels. Okay, if otherwise most of the time we ask in the exams single channel means or single service station type questions. Okay, so this is what that we have done, and this completes this session. We will be telling more things actually in the next class. Okay, so thank you very much for your kind attention.